Hello everyone, my name is Rachel. I'm an application engineer in mental graphics D2S Calibre. Today's topic, I would like to cover how to use Calibre for physical verification. Table of content. Today, we will have an overview of how physical verification works. We will cover some general introduction on Calibre process flow, Calibre hierarchical processing, DRC, some DRC extension tools and features, circuit verification process flow, how to run LVS extension, and ways to optimize your DAC using Calibre Interactive. Physical verification overview. As the process technology advances and enter into advanced nodes, we will encounter new challenges, which include context sensitivity, new rules like FinFET rules, some voltage-dependent rules, which is difficult to debug. New layers has been introduced, like cut OD, metal OD, metal poly. This, you can see, increases the complexity and numbers of rules as well. Mental graphics is a way of the complexity and the runtime performance as well. So, Calibre factory personnel and AEs work hand in hand with foundries to optimize their DAC to reduce runtime and at the same time optimize and improve Calibre engines as well. This is the IC design and layout verification flow. If you can see here, netlist will go through simulation, and the simulation will have custom layout, automated layout, and from here you have to go through the physical verification cycle. Each time once update netlist, you have to go through all this cycle again. Calibre tools involved in many stages throughout the design flow. You can see here cell design, analog block, digital, chip design, and tape-out. Calibre tools is involved, and here is the sum of the tools that has been used throughout each different stages or design. So you can see here offers backend tools which include parasitic extraction, XRC, exec, perk, design ref, Calibre interactive, Calibre RVE, and lots more. Today, I will cover DRC and LVS and offer some other insight of different enhancement productivity tools as well. Physical verification general introduction. In the basic Calibre process flow, there's two inputs that you need to do. Okay, command line options and SPRF. User have to give these two inputs in order for Calibre engine to run, and SPRF is provided by Foundry or in-house rule. SPRF here stands for Standard Verification rule format, which is the language for writing Calibre runtime. And from here, you provide design data. And after the run, you have report, result data, and you review it using Calibre RVE, and it will highlight in your reviewer, which include NetList, layout, or schematic. Calibre hierarchical processing. Calibre recommends hierarchical design. It is important for performance and safe runtime. As an input, hierarchical is important for performance, as cells with many instances can save runtime by checking the in-cells polygon relation just once. And it scales well as well. Calibre scales design database by cell, which more cells means better scaling. If your design has hierarchy in it, in the output, when you debug, the violation in that particular cells only reports once. And output, with hierarchical design, your layout preparation such as metal, all this VR insertion and other layer generation will because of the hierarchical design, it will reduce your file size and simplify your post merging and downstream processing. How to run Calibre DRC. Here is the golden rules provided by Foundry or your in-house design rule. You can see here there's a lot of layer definition and operation on how the layers has been used. Calibre Interactive is a GUI where you can run all the physical verification, which includes LVS, DRC, perk, and how you customize command file as well using SPLS language. So using Calibre Interactive, you can manually enter all this information or provide it using the GUI itself. And when you execute, it's the same as though as you use command line to execute. For this particular instance, if you click on the run DRC here, it will actually go through this command, these golden rules, and checks it, inserting all the necessary information which you inserted in your GUI in a text field, and it will run exactly as if you are using command line. Here, you can see every one of these options has a corresponding on how you can using command line to run. For instance, if you select the DRC hierarchical here, it will become hierarchy here. And when you change the GDS format, it will change in the rules file as well. When you insert the layout files, changes here will be reflected in the rules. After run is completed, you can see here that this is the transcript, which is the log file of the run. You can see all the options, customized options, default options that you set, and you can double check it to make sure that you are executing the run in a correct manner. And at the end of the transcript, you can see how many rules has been executed, operations, runtime, and the CPU use. And when you highlight it load it in RVE and highlight it, you will see all the highlighted in the layout. And there's a special feature here where if you include a CTO file in RVE, it will actually given that the information in the CTO file, you can actually highlight only the respective layers, and it will actually turn off all other layers that is non-related. For this particular case, VR3, you only highlight VR3 and turn off all other layers that is not related. This, you can see here, I'll introduce you to a less known feature, which is in area. If you just want to select violation in a particular area, you can do that in like this. Step 1, right click on that rule, select all. Then if you right click on the rule again and select in area and click on the area using your mouse in your layout, you'll actually select all the rules in that particular area. This step works for highlighting in area, fix in area, wave in area as well. Calibre equivalent DRC is an advanced SPRF where one can run equation-based or some special commands such as area, length, which you can use to output it based on calculations like parameter. You want to calculate your parameters for further post-processing usage. For this particular case, you can see S1 ratio, sum, error length. All these, if meet the requirement, it will output it into a text file, and you can see all these results. Here, in Design Ref, you could do layout comparison using FastXL. In interactive, you can easily load it here, run XL, FastXL. And this actually is a two-step process, two stages process, where the first stage, you make a dbdiff, which will do a cell-by-cell object comparison to exclude unchanged data. Then it will run the XOR, and the output is a ASCII file, result database, which you will load in RVE to see the comparison. This feature actually reduces hardware requirement, and it's fast as well. Here I will cover some antenna checks that is a compulsory check for tape out, sign off check for all other foundries. You can see here, antenna checks normally will use this command, net error ratio. Net error ratio actually calculates how all these metal add together to meet a certain requirement number. For this particular case, it's 20. If it's more than 20, then it violates. And it will normally output all the results into RDB, which you have all the numbers. You can see in the next slide here. If you load the RDB and click on the violation, you can see the value. For this particular case, it's 23.7767, which is much more than the 20. You can highlight it and see which part of the total area or the highlighted net, and you can see how you can optimize it or reduce some of the area to meet this particular requirement. Now we'll move on to circuit verification LVS platform. Calibre LVS continues to be the market standard verification platform from legacy nodes to the most advanced nodes. Here you can see the circuit verification where you have extraction from layout, or you design your netlist, and from the source netlist you can compare it and do LVS. And all these extraction can be used simultaneously or use it as a platform to connect to other third-party tools which might be useful. For instance, here you can see the LVS platform can use for reliability verification such as PERT, and this extraction verification actually uses some parameter extraction. Doesn't have to be Calibre tools. It does have this Calibre connectivity interface, which is useful to connect other tools as well. And here you can do normal physical verification, includes ERC. Run LVS as if you run ERC. Input, you just need input and output file. Here you just have layout, row file, and at the end you can have the extraction report and extracted netlist. After you extracted your netlist from the layout, you will do a comparison using the source netlist from the Verilog, and you have the LVS report and the result database. This is standard verification database. And you can load all this in RVE and review it in layout tools. This is the general idea on how LVS works. Layout versus schematic. How to run LVS. Here you can see in the Calibre Interactive, you just load the row file, insert the SPICE netlist file from the Verilog, insert the top cell, run whether you want to select hierarchical or flatten. Which step do you want? Layout versus netlist. And choose the corresponding format that you want. When you execute run LVS, the command line is actually equivalent to Calibre minus LVS minus hierarchy and the rule name. Hash cell. Hash cell is an important element for LVS. How well is the runtime depend on the hash cell list. You can input the hash cell in 3 ways. Auto match, custom hash cell list, or you can use SVRS command hash cell in your run set. Hash cell list sample here, and some of the feature that is supported is a one-to-one, one-to-many, many-to-one, but we don't support many-to-many. Here you can see if you do not have a good hash cell list, it will increase the extraction time, and a lot of hierarchy injection and promotion will happen. If you have a good hash cell list, then it will improve comparison time. Memory consumption will reduce as well. And here are some of the commands that you can use during your LVS run, which is gen hash cell will automatically generate hash cell based on the engine algorithm. And you can use this LVS auto expand hash cell field to expand some of the field cells that is not necessarily beneficial to keep as a hierarchical cell. Hash cell list preparation has 4 approaches, like I explained briefly. You can build as you go. That means bottom-up approach, where you run block level, you build a hash cell list, pass the information to a higher hierarchy, and all the way to full chain. You can use our built-in engine to find the cell with certain naming on convention using a tickle script, where you use this particular script during your command line or your using Calibre Interactive to run. You can use this feature as well, gen hash cell, auto match. And you can use hash cell analyzer after your first run. Then you use this analyzer to analyze the future, to generate a hash cell list for your future run. Hash cell recommendation. It is recommended to have a good hash cell list. And here's a white paper featuring why it's important and it is beneficiary for digital place and route. Moving on. Performance. If you can see here, in this particular graph, hash cell list impact runtime. If you have no hash cell, in a design one, it will be roughly around 4.5 hours. Using auto match, it reduced around a bit over 4 hours. And if you have a custom hash cell list, which is not optimized, it might be even worse than no hash cell. And you can see here in design 2, some of the jobs has been killed because there's too much information on how to promote or injecting hierarchy into the layout before the run. So generally, you can see here that using an optimized hash cell or auto match does improve how the runtime compared to a non-hash cell run. And you can see here, it also improves on the memory as well. So you can see here, if no auto match and no hash cell, you can see a large memory and runtime. Usually, it will be killed or did not finish. Auto match will use the lowest memory and runtime. It requires one-to-one corresponding cell and naming and structure. This is the first step. If you have no idea how to build your own hash cell list, maybe you can start off with auto match and build all from there on. Hash cell list to be optimum, you have to build your own. And the new solution here is you use gen hash cell list plus your hash cell. Short isolation is one of the features in Calibre LVS. It is without any modification to LVS deck. You just need to add -si in one of the options, And this one actually check for short. It will show you the shortest path on two of the, like for instance, power ground shorts and signal shorts. It will show you the shortest path and highlight it and show you as if you are debugging using DERC. It's a quick fix with fast iteration. Here is a command where you can add this short isolation during your LVS run. This LVS isolate short, default is no, so you can put it as yes. And the default is cell primary. That means you only recognize all the pins in top level. Here is an example of how the command is being used. You can do that interactive as well. You just need to enable output short by cell, and ideally it's the same. You just enable run short isolation, run shorts by cell, and other option. RUDEC customization. Sorry. LVS select short. You can see here, this when you load, this is the additional tab. You can see layout shorts after your LVS run. You can highlight it by net and it'll show this way. So you can see this one, the shortest path from point A to B. So for this case, it's VDD to VSS. It will show you the shortest path here. And if you have trouble finding what is the layers in one particular location, for this particular case is here, you can actually use this select from the layer. Click here, and you can select what you want. This is to choose what are the layers that you want to be you select for this short isolation. And from there, you can remove it. What layer you felt by removing that layer, it will fix the short. And after removing it, you can do a simulation virtual to verify your short. And if after removing, if it's fixed, then it will show it's clean. For this particular case, it's gray out, that means it's clean. If it's not clean, then it will actually report a new short. Let's say there's multiple short, you fix one short. After verifying the short, it will show the second path, the shortest path for LVS. So by removing that as well, you continue on to remove all the root cause of the shorts, and after doing some verification iteration, you will have a clean result. And here, everything is done using the SVDB. There's no layout manipulation at all. RUDEC customization. Calibre Interactive offers a lot of ways which you do not need to do it manually inside the RUDEC. For this particular case, let's say you want, there's a lot of options: define full chip, define with seal ring, define with polyimide, AP28K thickness. All these are the options. So you can customize in Calibre Interactive to have all these as a click button. So it's actually ease as a GUI to ease user and to reduce wrong selection. Let's say there's a few ways that you cannot select. For this particular case, you cannot disconnect all resistor and connect all resistor. So you cannot enable these two features at the same time. So you can customize it, and it will actually check how the if-else and the condition where which particular option can be used. And you can do that as well in Calibre run. So for instance, you can enable all these features, Calibre, front, batch, GUI sign off, all these, or you can customize it into different rule selection. All this can be done using Calibre Interactive. I will end my presentation here. Hope that the brief introduction is useful and will give you ideas on how Calibre DRC, LVS, and some of the tools works. There's a lot of things that I didn't cover. It is only a scratch of the surface. In the upcoming webinar, there will be a lot of in-depth topics and advanced DRC LVS that will be covered. Stay tuned. Thank you.